Having talked about how to describe the rotation of any point, we're now going to talk about the rotation of a rigid body. Alright, two coins rotate on a turntable. Coin B is twice as far from the axis as coin A. Which one has the higher tangential speed? Meaning, if they were to suddenly fly off, which one would be flying faster? Well, the turntable has a fixed period. It takes the same amount of time to go around, so they're each taking the same amount of time to go around. But B is covering a much greater distance, right? Because it's a bigger, sorry, it's terrible, but it's a bigger circle. And so it must be moving faster because if velocity is distance over time, and the time is the same, if that's more and this is the same, then the velocity is more. So B must have a greater tangential velocity. A similar but different problem. Two coins rotate on a turntable. Coin B is twice as far from the axis as coin A. Which of these is true? The angular velocity of A is twice that of B, or the angular velocity of A is equal to that of B, or the angular velocity of A is half that of B. The key insight here is to recognize that during one revolution, they go through the same angle, namely 2 pi. And they take the same amount of time because they're on the turntable, which is rotating at some fixed rate. So the angular velocity, which is the angle, right, omega is delta theta over delta t. This is the same over the same. So it must also be the same. Alright, so far in the class, we've been treating things as point particles. But now we'll start talking about extended objects, things that take up actual space, no longer infinitesimal points. We'll mostly concern ourselves with rigid body. A rigid body maintains the same shape as it moves, though it may rotate. And it can have several types of motion. It can have translational motion, where it just slides along a table or whatever. It could have rotational motion, where it just goes around its center, or around some fixed point, doesn't have to be the center. And every point executes a circle. Or it could be some combination where it follows some trajectory, but it rotates about a point while doing that. This is obviously the most complicated one, but can really be thought of as the combination of these two, and so therefore is not as bad as it looks. Here's the key insight. Since the rigid body keeps its shape, if one point rotates through some angle, all the other points must also. This means that every point on a rigid body has the same angular velocity. And that is really crucial. They share the same omega because they keep the same shape, which means they have the same relative orientation. Therefore, it makes sense to talk about the angular velocity of the object rather than having to worry about the angular velocity of each of the individual constituents. We define the angular acceleration, symbolized by the Greek letter alpha and measured in radians per second squared, analogously to linear acceleration, that is, alpha equals omega over t, the same way that A was delta v over delta t. Rashid and Sophia are riding a merry-go-round that is spinning steadily. Sophia is twice as far from the axis as Rashid. Sophia's angular velocity is what? That of Rashid. I don't know why poor Rashid's last letter got cut off. And the possible answers are half, the same as, twice, 4 times, or we can't say without knowing their radii. Since they are on a thing which is spinning uniformly, and they are moving with it, they're essentially part of that rigid object, which means that they all have the same angular velocity. Same setup. We have she is twice as far from the axis as Rashid. Sophia's, and we should be careful here, they mean tangential speed or linear speed. Either way, the idea that if they were to suddenly let go, they fly off. And we want to know how her speed compares to that of Rashid. She's twice as far out, so she covers twice the circumference as he does, but they take the same time, so her speed must be twice as large. Just like for linear motion, it is not the sign of alpha that tells us whether an object is spinning faster. It's how the sign of alpha and omega compare. If they have the same sign, the object is spinning faster. We'll sometimes say spinning up, although that's bad, probably bad notation. If they have opposite sign, then they are spinning slower. And again, you'll sometimes hear that as spinning down. But again, probably bad vocabulary because there's no up or down here in the physical sense. We just mean getting faster or getting slower. So, the fan blade is slowing down. What are the signs of omega and alpha? Well, you want to remember that our coordinate system by default is that plus theta is counterclockwise, but omega is this one. It's going clockwise, which is negative, so neither of these can be true. It's getting slower, so alpha must have the opposite sign to omega, so if omega has to be negative, alpha must be positive. A flywheel has both omega less than 0 and alpha less than 0. How is it rotating? A flywheel, by the way, is just really just a large disk, large heavy disk generally, used to store angular motion sometimes. Since omega is less than 0, then it's moving, we know, clockwise, so these are both out. And since alpha is less than 0, they're the same sign, so it's getting faster, so it must be this one. Because, again, math cares about the forms of symbols and not what they mean, the fact that we've defined the angular velocity and the angular acceleration exactly analogously to the linear velocity and linear acceleration means that the equations of motion will exactly map over, that we could just replace the linear variables with their equivalent angular variables and get a true statement. So, for instance, position x becomes angle theta, and velocity, which is delta x over delta t, becomes angular velocity, which is delta theta over delta t. And acceleration, which is delta vx over delta t, becomes angular acceleration, which is delta omega over delta t. And because these definitions are the same, all of the constant velocity and constant acceleration equations hold the same. So when we had, for instance, delta x is v delta t plus a half a delta t square, now we'll be able to replace each of these with their corresponding angular counterpart. So again, x becomes theta, etc. And we get a new true equation, which is delta theta is initial omega delta t plus 1/2 alpha delta t square, and so on. Starting from rest, a wheel with constant angular acceleration spins up to 25 RPM in a time t. What is its angular velocity going to be after time 2t? We note that, a little frustratingly, the speed is given in RPM, but then all the outbound speeds are given RPM, so we're okay. And we can say, well, omega is alpha delta t. So omega 2 would be alpha delta t2. We can see that this hasn't changed, but we've made this twice as large, so we must make that twice as large, 50 RPM. As with linear motion, the angular acceleration can be found as the slope of an angular velocity versus time graph. And the change in angular velocity can be found as the area trapped by an angular acceleration versus time graph. What is the angular acceleration of this object? Well, we want to find the slope. I'm going to take the slope by taking these two things. This is 5 rad per sec, and this looks to be 2 seconds. So the slope equals 5 radians per second over 2 seconds, or 2.5 radians per second squared, but that is alpha. A fan blade spinning at 560 RPM is brought smoothly to rest while rotating through 25 turns. Find the angular acceleration in revs per second square. And here we want to point out that, again, somewhat annoyingly, we're in RPM, but we want revs per second square, and turns, which is the same as revs. So we don't have to convert revolutions to 2 pi, but we will have to convert RPM to RPS. So let's do that first. Omega naught is 560 rev per minute times 1 minute per 60 seconds, which is 9 1/3 or 28 thirds rev per second. And then we're going to say, well, delta theta is omega initial delta t. Oops, nope, we're not going to do that one at all. we have no delta t information. So we're going to have to construct our earlier one. We might remember when we had no time information, we used to have v squared equals v0 squared plus 2a delta x. So this is now going to become omega squared equals omega 0 squared plus 2 alpha delta theta. We know that we're ending at rest, and we have 28/3 rev per second quantity squared plus 2 times alpha times 25 revolutions, because 25 turns and 25 revolutions are the same thing. We're going to solve over for alpha. Alpha is 28/3 revolutions per second quantity squared over 2 times 25 revolutions. And we're going to get 0.187 revolutions per second squared. A wheel starts from rest and begins to accelerate at a constant 5 radians per second squared. Through how many turns does it go in the first 20 seconds? And here, finally, we are in conflict. We have turns, but we have radians. We'll have to convert 1. So I'm going to get it in radians and then figure out how many turns it is. All right, well, we have, looking at this, we want position information, stuff about theta, and we have an initial velocity, and we have an acceleration. So we're probably going to want to use that delta theta is omega initial delta t plus 1/2 alpha delta t quantity squared. So over here we'll say delta theta is, well, it starts from rest, so that's good. And we have 1/2 times the 5 radians per second squared times 20 seconds quantity squared, which is 1,000 radians. But then there is 1 revolution per 2 pi radians. So we divide this by 2 pi, and we get 159 turns. If omega is changing, then the linear speed of the object must also be changing. There's a tangential acceleration, which turns out to have an easy expression. The tangential acceleration is r times alpha. Don't confuse this with a sub c, the centripetal acceleration. So what is the tangential force acting on a 25-gram object on a disk 20 centimeters in diameter, spinning at 4 radians per second and speeding up at 15 radians per second square? Answer in newtons. We're going to, of course, go back to that the force here is going to be ma. We want the tangential force, so we'll take the tangential acceleration. The tangential acceleration is r alpha. So if we want to be in newtons, we should make everything in meters and so on, and kilograms. So here we have, we have 15 radians per second squared. So our tangential acceleration turns out to be a nice easy 3 meters per second squared. And then our tangential force is 25 grams times 1 kilogram per 1,000 grams times 3 meters per second squared, or 0.075 newtons.